Hi, this is Paul again. I'm calling this video 3D Printed Platonic Order Phi HEXPENT 2 Toy Primitives. In my last video, Phi HEXPENT 1, I showed in the end of my video a hub with the vectors for the icosa all in color. So let's take a look at it again. So as you can see, the vector sticks, the colored sticks on the hub turned out pretty good on the 3D printer. I use a Dremel 3D printer. When it comes to the hub, I just print one primitive solo. But when it comes to the sticks, I've started printing 12 at a time. I put them all vertical and print out 12 at a time, and they come out pretty good. But I can only do one color at a time. So this stuff takes a bit of time to do. I think the sticks could be turned out by injection molding. But when it comes to the icosa hub, I would say that would be some complicated mold. So this is where 3D printing comes into its own. So to be able to turn something like this out without having to put all the money up to build a mold is fantastic. Now, to tell you the truth, I started designing nucleosomes. But when it comes to this geometry, I realized this little toy is more important because nobody was interested in my nucleosomes. So my first job was to build my first bend. Now, my first attempt, I found the bend was a little bit flimsy. So I decided to do some modifications and try to beef it up a bit. So this is how the beef bend was invented. I first designed this bend to fit between two nucleosomes. That is why the sleeves are short in length and I show a chamfer just to fit in between the nucleosomes. I have modified it for the toy, so we'll show that later. Now this bend is an obtuse angle. It's over 90 degrees. Now this is because in my earlier videos of research, I found that the dual helix would not go around a bend unless it was obtuse. Now a configuration of these vectors will make a hexagon. But this angle, when you look down at the hexagon, you would think it's 120 degrees. But in fact, the vectors are sloping to each other, so it's not exactly 120 degrees. So I think I'd better show you this on the toy. Because now I'm showing my work in reality, because a mathematician said that my geometry was too trivial for them to understand. Anyway, take a look at this hexagon. Now all these colored vectors correspond to the vector orientation of the icosa. Now notice two matching colors are parallel to each other. If you look at this hexagon, the center axis is a dodeca vector. So what I've done, I've put a little bit of research into this, and this is what I've found. Now take a butcher's at this. This is something extraordinary. Now each of these red, cyan and green vectors are all the same length. Isn't that something? Because what I've done, I took the center of the icosa to the vertex and I doubled that length. So this is an easy way to find the dodeca vector of this hexagon. So when I woke up yesterday morning, I was thinking about this and I thought, what about the 369? What happens with that? So I done exactly the same with the orange, purple and blue vectors. So I played around and made copies of these vectors and put them together again, and look what I found. So as you can see, it forms a perfect rhombic shape. And you can see that the yellow and cyan vector, dodeca vector, is running as a diagonal through this rhombic, is also the diagonal of a pair of cubes going ratio to each other, the yellow and cyan. Now this arrangement can keep on stringing along that vector for as long as you want. I would say that this is connected to sine waves. because even though they show us 2-dimension on an oscilloscope, I showed in a few years ago that the sine waves are actually 3-dimension. Okay, so let's get back to the little toy. So now we know that the hexagon made of red, green and cyan vectors use the yellow and cyan vector of the dodeca as a center axis. Now I showed in my earlier videos, if you want to form a spiral, you're going to have to use the dodeca vectors and the icosa vectors, a dual vector system. Now you can see that these dodeca vectors line up orientation the same as the center axis. When I done some earlier research on a nucleosome, I found that that dodeca step was exactly the same as a size 1 cube, which was 100 I always use. So it was 173, because we're looking at the diagonal. So that would be root 3 of 100. Now because I'm working with a toy, this is not exactly to scale, but the orientation of the 5 vectors are pretty close. So now I'll show you the dual vector bend that I've made for this DNA type spiral. Now I mentioned earlier about the beef bend, it was obtuse. But if you study this bend, you'll notice that the top half is obtuse and the bottom angle is acute. Now this is the reason I think that the geometry of the nucleosome drops 1 rung from 16 to 15, and that makes 1080, which is 3 times 360. 3 times 360 looks spot on to me. So now I'll show you the 3D spiral that came from the 3D printer. I think this will make it a lot easier for children to understand how nucleosomes go together. But I think construction toys are not very popular like they used to be years ago. But like I said earlier, 3D printing might help to change that a little. I've made another connection piece, and this is a straight connector. So I'll add another vector with this connector and make the hexagon look like a nucleosome. Well, just 1/2 of the nucleosome. Because I found that the nucleosome adds another section like this as a mirrored version. I've put some prototypes together, but I'm more or less concentrating on this little toy first. So now I'll take you back and show you the inline connector in more detail. Now if you notice that connector, one side is 180 degrees difference to the opposite side. Well, actually the pentagon needs to be twisted 36 degrees, and this shows up the same. Now notice that I use the numbers for the 369 and the sequence. I used the same sequence 147, 258 and 369 on the dodeca and the icosa. It looks like the sequence works the same. Anyways, I think we'll call it a day on this one. So this is Paul saying thank you very much for watching my video.